Alright, so number 4 on your assignment from last class. So what we're going to do first is we're just going to draw a quick picture just to kind of help us visualize what's going on. Okay, so I want you guys to do this for your assignment problem as well. So it tells us that we are combining 0.5 grams of O2 with excess N2 gas. So let's label a box for our start. Okay, so this is going to be pretty much our starting container. And inside of our container, it tells us we have 0.5 grams of O2. So we're just going to write 0.5 grams of O2. And then we are combining that with excess N2. Remember, excess means you have so much of it, you don't need to worry about it. We kind of just need the information for the balancing. So we're going to write excess N2. Okay, so these two chemicals are reacting together. All right, and so what's happening is they're going to combine, and that's what this balance equation is telling us. And then we're going to draw an arrow to show that this is what's going to happen, and this is going to be our end point. And when these chemicals combine, we are going to end up with the chemical NO. So we're going to write NO. Okay, so O2 and N2 combine to make NO. And so what we're trying to figure out first is energy going to be absorbed or released. And this is what we learned last time. Okay, now, if you guys take a look at energy, it tells us that the enthalpy of the equation is 180.6 kilojoules. So what we have to look at is this a positive or negative number? So this is positive, so is energy being absorbed or released? It's being absorbed, okay? So just keep that in mind. If it's a positive number, it means that it is endothermic. Energy is being absorbed. If it's a negative number, it's exo. It's being released. So in this situation, energy is being absorbed. So on our picture, we're going to draw some arrows going in to the system, because what is happening is energy is being absorbed. So as O2 and N2 combine together to make NO, it's going to pretty much take energy into the system. That's what this equation is telling us. Okay, so I know it just looks like letters and numbers sometimes, but there's a lot of information that is given to us in that equation. Okay. All right, so that's our picture. That's also our answer to part A. Energy is being absorbed. Okay. All right. Any questions on that one? Hopefully not too bad. Understanding it. It's just the endo-exo stuff. Okay, so let's go over the stoic that we learned last time. Basically, is energy being absorbed or released? Okay, so or how much energy, excuse me. So in order to solve this part, the first thing that we need to do is we need to balance this equation right here. So I want you guys to take a minute, just write this down on your paper, because we're going to be balancing it together. So I'll give you a minute to copy down the equation on your paper. Okay, so to balance, what we want to do is we want to figure out what elements are inside of the equation. So we just look for the capital letters. So it looks like we have a capital N, so we got some nitrogen. We have a capital O, so we got oxygen. So those are the two elements that are inside of our reaction. So let's count how many of each we have on the left versus the right side of the arrow. Okay. So if we look at the left side of the arrow, you're going to see a 2 next to the nitrogen. So there are 2 nitrogens. If you look at the oxygen, there's a 2 next to oxygen, so we have 2 oxygens. We got 2 of each. All right, let's look at the right side. If you take a look at the right side, we got capital N and capital O, but there's no numbers next to them, so that just means we have 1 of each. So what this is telling us is that we need more nitrogen on the right side, and we need more oxygen on the right side. God bless you. Okay, now, this is a pretty easy balancing, because all we got to do is add more of what we already have. So we have NO. If we add another NO, now we're going to have 2 nitrogens and 2 oxygens. And so if you guys take a look now, we got the same number on both sides, so it's balanced. So for our blanks, we just need to put 1, 1, and 2. And that's going to be our balancing. Okay, and again, this is what we learned last time, the new stoichiometry. So for the new stoichiometry for enthalpy, we're going to write down our starting number. If you guys look at the problem, the starting number is 0.5 grams of O2. That's how much we're starting with. So we're going to write down 0.5 grams of O2. And we are going to set up two fractions. So I'll give you guys a minute to copy that down. Okay, and then I'm going to give you guys the labels. And then if you feel comfortable filling them in from what we learned last time, you can do that. But if not, that's totally fine. You guys can just copy down the labels for right now. Okay. Okay, so we have the labels and we have where we're getting the information from. So for this first fraction, we're going to get the number from the molar mass of our starting chemical. Our starting chemical is O2. So we're going to go on the periodic table and find the molar mass for O2. Okay, so if you guys have your periodic table, you guys can pull that out. But this is our periodic table, and O2 is made out of oxygen, right? So we just look for oxygen, and we look for the number on the bottom. It's 16, but there's two of them. So 16 plus 16 will be 32. So the number from the periodic table is 32, and we always put that next to grams because O2 is 32 grams, and molar mass by definition is the weight or the mass of 1 mole. So 1 mole of O2 weighs 32 grams. So this position, if you guys want to make a note, is always going to be 1. Okay, so you'll have 1 over 32 because it's 1 mole of O2 is going to weigh 32 grams. Okay, so that's how you fill in the first fraction. Okay, again, molar mass is periodic table. All right, second fraction is pretty easy. We look for the chemicals on the balanced equation. So we're looking for O2. So if we take a look at O2, you'll see the number in front of O2 is 1. This is why we balanced to begin with. It's for this fraction right here. So 1. So we're going to put a 1 right here on the bottom. Okay, and then the problem is asking us for energy, so that's why we're ending it with kilojoules. And so if you take a look, the number for kilojoules is 180.6, so we plug in 180.6 right here. All right, and all we got to do now is plug it into our calculator. So if you guys have your calculators out, just to practice using it, just remember all the numbers on the top you're going to multiply. All the numbers on the bottom you're going to divide. Take a minute, plug it into your calculators. Let's see if you guys are able to plug it in correctly and get the final answer. All right, guys, so if you go left to right, you'll do 0.5 divided by 32 times 180.6, and you should get about 2.82. Okay, so we're going to write down our final answer. It's going to be 2.82, and remember the label, since we're looking for energy, is going to be kJ or kilojoules. Okay, so this is going to be your final answer for part B. Okay. All right, any questions on how to plug it in? That part's not too bad. Again, it's the same type of math we've been doing. Multiply the top, divide the bottom. All right, so let's go back to the picture that we drew in the beginning, right? The picture was telling us if you combine 0.5 grams of O2 and excess N2, you're going to make NO, and the system is going to absorb energy. Well, the math that we did is basically telling us it's going to absorb 2.82 kilojoules of energy. That's the amount of energy that's going to go into the system. Okay, that's what this math is about. It's telling us how much energy is going to actually go in. It's giving a number to the concept we already know. We already know it's absorbing energy, but we're figuring out how much energy is being absorbed. Part C is just regular stoichiometry, and what part C is telling us is another component of what's going on in this system. So we just figured out how much energy is going in, but if you guys remember, we're making a new chemical, right? We're making NO. So part C is pretty much asking us how many grams of NO is being made. So now we're trying to figure out how many grams of the product we're making, because that's the two important things. The first is the energy. The second is how much of the chemical we're going to be making. Okay, so this is just regular stoichiometry. So I'm going to show you guys how to set up the fractions for this. Okay, so we're going to take the same starting number. So it's 0.5 grams of O2. So let's write down 0.5 grams of O2. And for regular stoichiometry, you're going to need 3 fractions. So let's set up 3 fractions. This is the first type of stoichiometry we learned all the way back in October, November-ish. Okay, so 3 fractions. Okay, and I'll give you a minute to copy this down before we start explaining how to fill it in. All right, guys. So let's start plugging in our numbers. So first fraction, if you guys take a look, it's the same as this one right here, right? It's the moles on the top, our grams of our start on the bottom. So for this one, just to make it easier for yourself, you can just copy it from part B since you already did that work. It's the molar mass of our starting chemical, which is O2. We already figured that out as 32. We added 2 oxygen, so that's 32. So this fraction is the same thing as this fraction right here. Okay, so you don't need to do double the work. Okay, so we're going to go to the second fraction. The bottom is the moles of our starting chemical. The top is moles of ending. And we're looking at the balanced equation. So we're going to look at the balanced equation. Our ending chemical is N2. Sorry, not N2, excuse me. We're looking for NO, right? It's asking for NO. So we look for NO. The number in the front is 2. So we put a 2 on the top. Our starting chemical is still O2, and it's a 1. So we're going to put a 1 right here. All right, so that's the second fraction. The third fraction is the only one we need to do a little bit of extra work for. And this is the molar mass of our ending chemical, which is NO. So if you guys remember, molar mass is the weight of 1 mole. So this position right here is always going to be 1 for this regular stoichiometry. So if you want to make a note of that, molar mass by definition is the weight of 1 mole. And all we got to do now is go to the periodic table and add up the molar mass of NO. So I'll give you guys a minute. I want you guys to go to the periodic table, find the molar mass of NO, and see if you guys can fill in this spot right here. And then once you get that, you can just solve all the way through. Again, multiply the top, divide the bottom, and that'll give you your final answer. So let me give you guys a minute to do that. At least try to get the molar mass of NO, and then we'll review the final answer. All right, guys, so let's take a look at NO on the periodic table. So if we take a look at NO, we got nitrogen is 14.01. Oxygen is 16. This is nice because they're right next to each other. So we add them up. That's going to give you 30.01. So 30.01. And that's going to be our entire setup. So if you guys look, we already did most of the work for this already. We're just kind of, the only thing we really had to do extra is this last fraction right here. All right, let's plug this into our calculator, and then we will be all done. Okay, so we're going to go left to right. So 0.5, again, multiply the top, divide the bottom. For this first fraction, there's a 32 on the bottom, so divide by 32. For the second fraction, we got a 2 on the top, so times 2. And then 30.01 on the top, so times 30.01. And you'll get a final answer of about 0.93. If you rounded that to 9.4, that's fine as well. I'm going to round it to 9.4, but you don't have to. And it'll be grams of your ending chemical, which is what you're looking for, so NO. Okay. All right, so what all of that is telling you is that when you mix 0.5 grams of O2 and N2, you are going to be making, the system is going to be absorbing 2.82 kilojoules of energy, and you will be making 0.94 grams of NO. So what we are figuring out is how much energy is involved in this reaction, but also how much of a different chemical we're making. Okay.